Welcome to This Explainer. Today, we're diving into one of the most fascinating, high-impact, and honestly, ancient sciences out there. Think of it kind of like the ultimate strategic matchmaking process. We're talking, of course, about the science of animal breeding. And look, this isn't just about tossing two animals together in a pen and hoping for the best. It's a highly calculated, deeply scientific endeavor that literally sustains global agriculture, and really, human civilization as we know it.
So, right off the bat, here's the big question we're tackling. How do we actually go about engineering the perfect herd? How do we step in and actively intervene in these biological processes to create better, more efficient animals to feed the world? It's a huge challenge. I mean, every single glass of milk, every carton of eggs, and every piece of meat at the grocery store is the direct result of generations of incredibly calculated genetic decisions. Today, we're going to unpack exactly how those decisions are made.
Here's our roadmap for the day. First, the goals of animal breeding. Second, the mechanics of inheritance. Third, natural versus artificial selection. Fourth, we'll look at three core selection methods. And fifth, identifying superior breeding stock. Let's get into it. Section 1, the goals of animal breeding. Before we get into the how, we really need to nail down the what and the why. The definition of animal breeding is actually wonderfully simple. It's just the application of animal genetic principles to improve animal performance. Now, notice that word improve. That's not random. That is the entire foundational goal of manipulating these biological traits. We're basically taking the hard rules of genetics and using them as tools to purposefully build an animal that performs better than its parents did. When we say we want to improve performance, we're laser focused on three primary outcomes that directly affect our food supply. First up is quantity. We want more output, right? More milk, more meat, more eggs. Second is efficiency of production. This one is absolutely crucial for keeping things affordable. So, can an animal produce that higher quantity while eating the same amount of feed, or maybe even less? And third, we're looking at the quality of the animals and their products. We don't just want more, we want better. Basically, everything a breeder does circles right back to these three main targets. To actually hit those targets, breeders rely on a couple of critical parameters. The first is heritability. You'll usually see this written as H squared. This is the portion of phenotypic variation, meaning the physical traits we could actually see that's due to heredity or genetics. It's the stuff that gets passed down from parent to offspring. Then, on the other hand, you have repeatability, or R. This refers to the expression of the same trait at different stages of life in the same individual animal. Think of a chicken consistently laying eggs year after year. So, the main takeaway here? Heritability is about what passes to the next generation, while repeatability is all about consistency within one single animal's lifetime. Now here's the catch. Heritability isn't just a flat rate across the board, and that fundamentally shapes a breeder's entire strategy. Production traits, like how fast an animal grows or how much milk a cow gives, those are moderately to highly heritable. That means if you breed two high-producing animals, you've got a really solid chance their offspring are going to be high producers too. But reproductive traits, like litter size or fertility, those are lowly heritable. They are way harder to pass down consistently and get influenced a lot more by the environment. Knowing that completely shifts how a breeder has to approach the genetic equation. All right, Section 2, the mechanics of inheritance. Now that we know our goals and parameters, it's time to look under the biological hood. This is the literal flow of genetic materials. Step 1 is the overarching process of reproduction, which covers all the physical and physiological processes from fertilization straight through to the development of the young. Inside of that, we have Step 2, where the magic really happens, gametogenesis. This is the creation of sex cells, spermatogenesis in males, oogenesis in females. These cells carry half the genetic code. Finally, Step 3 is fertilization, which restores the diploid chromosomes. In plain English, it takes those two half codes, snaps them together, and creates a brand new full genetic sequence. This right here is the biological canvas breeders get to paint on. Moving on to Section 3, natural versus artificial selection. So we've got the biological mechanics down. But how do we actually make the active choices? It all boils down to one word: selection. This is simply the process where certain animals are preferred for the production of the next generation. It is the absolute pivot point where the matchmaking begins. Out of 100 animals in a herd, which two actually get to pass on their genetic material? Now, obviously, nature has its own way of doing this through natural selection. It's your classic Darwinian survival of the fittest, where the environment dictates who lives long enough to breed. But artificial selection is what we're focused on today.
This is direct human intervention. We're stepping in and deciding who breeds, specifically to improve existing breeds and strains for our own agricultural goals. We're basically bypassing nature's passive method so we can engineer better genetics and do it a whole lot faster.
Section 4. 3 core selection methods.
So, if we're the ones in charge of this artificial selection, what strategic systems are we actually deploying to pick the genetic winners? Well, there are 3 main methods. First up is the tandem method. This is where you're aiming for genetic progress across 2 or 3 traits, but you only focus on them one at a time. You fix one trait, get it right, then move on to the next. Next, we have independent culling. Think of this kind of like a stripped reality TV audition. You set a specific standard for, say, 3 different traits. If an animal fails even one of those standards, boom, they are entirely rejected from the breeding pool. It is brutal, but it works. Finally, there's the selection index. This one is highly mathematical. You're selecting for multiple quantitative traits all at the same time, but you assign them different levels of importance, or weights. You're basically creating a master score for the animal. It's definitely the most sophisticated way to juggle multiple goals at once.
And finally, Section 5, identifying superior breeding stock. Okay, so we've got our selection methods, but those methods are useless without data, right? Where do we actually get the info to make these high-stakes matchmaking choices? Finding superior stock is basically genetic detective work, and breeders look for clues in 4 distinct places. First, individuality. You literally just look at the animal in front of you. Its phenotype for a particular trait. Is it big? Is it healthy? Second, you check the pedigree. This is the ancestor record. You're looking for an animal that is pedigree clean, meaning a family tree with no history of bad genes. Third is the progeny test. Here, you evaluate the animal based on the performance of its offspring when they're put through a standard test. You're literally judging them by the kids they produce. And fourth, collateral relatives. This is where you look sideways on the family tree, checking how the aunts, uncles, and half-siblings perform. By gathering all these clues from the individual, the past, the future, and the extended family, a breeder gets a really complete picture of an animal's true genetic worth.
The absolute holy grail of all this detective work is a concept known as specific combining abilities. You'll sometimes hear breeders call this nicking ability. It's what happens when certain traits an animal has combine exceptionally well with the traits of another. It factors in this incredibly complex reality that genes actually affect how other genes are expressed, and they all interact with the environment on top of that. It's about finding that perfect, harmonious genetic match where the offspring turns out to be dramatically better than just the sum of its parents' parts.
So there you have it. We've walked through the goals, the cellular mechanics, the strict selection methods, and the deep detective work it takes to engineer animal genetics. It is a rigorous, deeply scientific process that we've been refining for centuries to make sure grocery store shelves stay stocked and our world stays fed. But as our global population keeps booming and our environmental challenges pile up, I want to leave you with this question to ponder. How will these ancient principles of genetics and selection continue to shape the future of agriculture and ultimately human survival? Thanks for joining me on this explainer, and I really hope it gave you a whole new appreciation for the incredible science behind the food on our tables.